Okay, let's continue with our lecture of 9798. Sorry, I let this get back to the beginning here. So, quick review. Da-da, 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 da-da. Know how to do the reactions. Nice little diagram. And at the atomic level of how this occurs. But the real key to this whole thing is this exchange of electrons that is a thermodynamically favored process. And that is your basic battery. That's how they used to say it in Stearns County when I went to St. John's. I'll tell you right now, that's your battery. 2 syllables, battery. All right, now, what is the purpose of the salt bridge? Well, let's go back. We talked about this a little bit, about how the ions can continue to move through there. But a real effective battery, it is important to keep a separation. The first battery that they made, they just used a little piece of cloth that was soaked in salt water in between the pieces of metal, and then they made a big stack, which made a relatively strong and effective battery, but it's not going to last very long. So a true salt bridge contains a gel with some type of ions that are definitely very soluble. Nitrates are often used, sulfates, and then you're going to want to go with family 1 cations. They got to make sure they don't react with the metals that you have, so they don't play a direct role. However, and that's what I just said here, you just want to make sure they don't react. And then ions from the salt bridge keep the solutions neutral. All right? If the solutions do not remain neutral, the reaction goes down like that little ball in the ramp, and then eventually slows down and stops moving. Okay? What you want is to continually pull the reaction forward by keeping those reactions neutral so that it continues to be a spontaneous process. Okay? So this is a closer look as to what's happening with the salt bridge. You can make sure you think about this as having both positive and negative ions in here. The dark green sodium ions, those were in there to begin with. Those are in your gel, but they kind of create a movement. Notice here the light green ones are moving in this direction, and that is what allows that negative charge to keep coming through. Eventually those sodiums will work, or those zincs will work their way up in with the sodiums here, and that's what that diagram's recommending or showing. But this right here with this, these light green sulfates kind of beginning to move in that direction, is key to understanding a salt bridge. And remember, you look for the circuit. Okay, anode and the ox, you're losing electrons, oxidation, out they come. You're gaining electrons right over there, and you have a red cat, reduction, a red cat. Okay, so this will continue to go on, and then you'll end up with some Na plus ions in here, and they're not going to do anything. They're not going to throw anything off, but they will keep the balance of charge as these coppers start to disappear and become solid copper, which is got to be the driving force of the reaction, right? Here they had lost electrons. Now they're going to gain them back to be a solid chunk of copper, and then these sodiums will come and fill the space when that happens. Okay, so 2 sodiums will come out and fill the 1 copper that went out there. All right, and over here you're making these excess positive charges, so they're going to need to work their way up into the salt bridge. Okay, so why do electrons flow from the anode to the cathode? Okay, and that, just remember alphabetical order, anode to cathode all the time. And that is because the potential energy for electrons is higher at the anode than at the cathode. And that kind of is that activity series thing that we've talked about since you were in 9th grade probably. All things naturally move to achieve a state of lower potential energy. Okay? A rock will fall naturally to go to a lower state of potential energy. So right now, the anode has more energy. Okay, so you can think of the ox, as being very, very energetic in terms of potential energy. Great big old the ox has all that potential energy. So that'll help remember that. Okay, what is this? Apparently he's an anarchist. That's those Canadians for you. As a big yo-yo or a rock tied with rope. There we go. That's what it is. The rock tied with rope. If you were going to lift this up, you would be fighting F equals mg, the mass times the force of gravity. A lot of times that equation is one of Newton's laws called F equals ma, the acceleration due to gravity, which of course is about 10 meters per second per second. So there's your distance. Work equals force times distance. So up here, you've got more potential energy. Okay? So potential energy final is the work that you did to fight that, and that's how you get that. Now that's going to work for us at the atomic level as well. So you're going to talk about the potential energy, which is electric potential energy, by the potential difference between things, and that's the change in volts, which is the potential energy, which can be measured in joules, and then this very unique charge unit. On your purple sheet, one electron has negative 1.60 times 10 to the minus 19th coulombs. We always just say -1. Okay? And it would take this many electrons, which is a lot, to give a -1 coulomb of charge. All right? So if you wanted a full coulomb, you're going to have a ton of electrons right there. So one electron has very, very small negative charge. And remember, that's equal and opposite the charge of a proton. But we can measure it in something called the coulomb. And we have done that before when we talked about intermolecular attraction and things along those lines. Okay? So here's your 12-volt battery, and you got the cathode and the anode. Let's instead of a rock, let's say there's this many electrons. Now, the potential difference, which is the change in voltage, is the change in electrical potential energy. All right? So it would take 12 joules of energy to pull this many electrons up here, because that's going to be 1 coulomb. And remember, it was joules per coulomb of charge. And this, you would have the 1 coulomb if you have that many electrons stacked up. So that's how many, in terms of joules that would take. Okay, so 12-volt battery takes 12 joules if you had a -1 coulomb of charge, or a whole bunch of electrons moving through there. Sort of gives you a perspective on this. All right, and then once that has moved from the cathode once you have it up at the anode here, that's where we have the higher potential energy. All right, now possesses 12 joules of potential energy, which in comparison to the cathode down here would have the potential to go down and actually create that 12 joules per coulomb, or 12 volts of power coming out of that battery. All right, so ultimately that means voltage is energy per unit charge. All right, the energy here is the difference in potential energy between the anode and the cathode. All right, so underline potential energy, anode and cathode. We already talked about this on the previous slide, the charge of one electron. And we also talked about this, how many electrons it would take to be that 1 coulomb. So this is just a summary up to this point. 12 volt battery, 12 joules per coulomb. So there gives you your conversion. I think highlighting this whole line would be worthwhile because that's what summarizes the previous slide. All right, and then the amount of work you did to get out there, that's how much potential energy it's going to have. That's just kind of restating what that diagram showed us. All right, now there are some terms here that come along with this. One is called EMF, or electromotive force, the force that causes electrons to move. And then we'll talk about a standard, and when you think of standard electromotive force, you go, okay, that's probably going to be standard conditions. Good instincts, we've talked about that before. Yeah, 1 molar concentration, 1 atmosphere partial pressure, 25 degrees. Now, we're going to call this the cell potential. A lot of times we call this E0 of the cell is the standard cell potential. So at standard conditions, how much potential is there to produce electricity? And then that is basically going to be the voltage of that cell. You guys might remember making your own batteries, and that's what we measured. We had that battery competition. You may have been in a group that was in first place in that competition. It's kind of a fun lab. But you can make power by having the different metals and the electrons moving through there. All right, so standard conditions, highlight that, and of course reactants and products are going to be at the same conditions in this particular thing. All right, now here's the thing. Actually, we are going to stop right here because this is a really good start for the next video, which we will do tomorrow. Okay, so we'll post a couple more videos on this unit on Tuesday or tomorrow. Okay, all right, so hopefully you got a good overview. That voltaic cell picture, super important. Get that kind of ingrained in your head. That will be very helpful as we move forward. But we're going to start crunching some numbers here and doing cell potential. So how can you figure out like that zinc and copper cell that we made? Scientists can tell you that's 1.10 volts. So how do we do that? And that's what's going to be coming up next. Okay? So, electrochemistry. You now have a minor in electrochemistry, and we'll get your major in that tomorrow.